All right, it's my great pleasure to welcome Jun Le Goh from our very own University of Wisconsin. He'll talk about joint work with a number of people on the extension of embeddings in the Sigma02 enumeration degrees. Jun Le?
Hi everyone, thanks for coming and thanks to the organizers for inviting me. I will speak on joint work with Stefan, Keng-Ming Ng, Xiaowin, and Maria Soskova. Now you might have heard Stefan speak on this before, but since then, we figured out a couple of other things. So in the second half of my talk, I hope to get there. But I'm not assuming that you've seen Stefan's talk. So we will begin from the beginning of the story, so to speak. All right, so first I want to tell you, well, what are the enumeration degrees? Well, so what is, these are the degree structure formed by taking enumeration reducibility. So if you have two sets A and B, sets of numbers, then we say that A is enumeration reducible to B, written A less than or equals to EB, if every enumeration of B computes an enumeration of A. So this is equivalent to the standard definition. Various authors first considered such notions in the 50s. So just seeing this for the first time, well, I like the following example of an enumeration reduction. So say we have a computable graph, okay? So it's a graph where you can tell in a computable way what's a vertex, you can tell in a computable way what's an edge, then fix a maximal independent set of vertices in this graph. So independent means that any two vertices in the set are not adjacent, and it's maximal in the sense of set inclusion. So let's call this capital B. Then the complement of capital B is enumeration reducible to B itself. Well, how do we do that? Well, let's say we're given some enumeration of B. Well, whenever we see something go into B, we know that all of its neighbors must go into B complement because of independence. Now, so this gives some kind of reduction, right? But what is its output? Well, the output is actually the whole of B complement because of maximality, right? If something wasn't produced by this procedure, then we could have added it into B in the first place. So B complement is enumeration reducible to B, as I just described. But in general, the reverse reduction does not hold. And I'm not proving this, but that's a fact. And so with this notion of reduction, right? So it is a notion of reduction in the sense that it's reflexive, it's transitive. So we can define the enumeration degrees by taking the equivalence classes of the, whenever A is reducible to B and B is reducible to A, they are in the same equivalence class, the same E degree. So in the same way that the Turing degrees are defined using Turing reducibility. And as you might expect, they form an upper semi-lattice partially ordered by this E reduction. And there's the usual joint operation is also a joint with respect to this reduction. Now, there is quite a bit more to say about the E degrees if we want to, but actually for most of this talk, I'll just be focusing on the E degrees as a partial order. So really, we can skip a lot of the preliminaries here, and I would just say that the Turing degrees embed into the E degrees in a natural way. You send each set A to the set A joint A complement. And you can show that this is a nicely well-defined operation because of this fact. And so we get an embedding. And it embeds as a proper subset. So there are E degrees which are not in the range of this embedding. But again, I think this is not going to be super important for understanding what I'm going to say. Okay, so E degrees as a partial order. Well, what are the questions that we can ask about a partial order? Here's one: is it linear? Right, that's a very natural question. More generally, so of course, all of these orders, right, these are the E degrees, they are not linear. So more generally, we can ask, well, which finite partial orders embed into this structure, this order, right? This question 2 is a generalization of question 1 because question 1 is the question of whether you can embed the two-element anti-chain into the order. Another question that you might be interested in is the question of density, right? So between any two, which are comparable, can you find a third one? Right, that's the question of density. And more generally, we can say, well, given any partial order, any pair of partial orders, finite, P subset of Q, if you have an embedding of P, can you extend it to an embedding of Q? Now again, question 4 generalizes question 3 because you can take P to be the 2-element chain and Q to be the 3-element chain. Okay, so you're trying to say, okay, can you, well, I mean, so Q is a 3-element chain with an extra thing in between. Yeah. So you're trying to say, okay, between two things, can you stick something in between? So these are, natural questions that we can ask. And question 5 now is going to be a different kind of question, a vast generalization. So, well, all of these questions, 1 to 4, we can view them as first order sentences in the language of partial orders. Okay, all of them can be expressed in the first order way. And the question here is, well, can we decide if these are true or not in an algorithmic way, right? Can we compute? If I give you a sentence, can you compute whether it's true or not of this partial order? And well, so the answer for 5 is almost always no, and specifically for the degree structures that we care about, the answer to 5 is no, as was first done by, well, okay, I'm not sure who did it first, but certainly Slayman and Wooden studied this for many degree structures. Okay, now I said that, well, the talk was supposed to be about Sigma02 degrees, so that's what we're going to focus on. Oh, sorry, I haven't got to that part yet. Now, so we can't decide in general whether a first order sentence is true in whatever degree structure. But let me comment that if you have a simple first order sentence, namely a first order sentence of this form, we have a bunch of existential quantifiers followed by a Boolean combination of the ordering relation. If you have a sentence of such a simple form, then we can actually compute whether it's true or not. And the reason is because, well, every finite partial order embeds into the degree structure. So in this case, well, the E degrees, but it's also true of all the other degree structures. So all we have to do to check whether this is true is we can check whether it is consistent with the axioms of partial orders. Okay, so if the Boolean combination of the ordering is not consistent with the axioms of partial orders, then obviously this is false, right? They cannot exist such A0 to AN. On the other hand, if it is consistent, well, then we can embed it into the E degrees, and that's a witness that this existential statement is true. So that's a nice algorithm to do this. And so the central question that we're interested in here is, well, at what point does computability break down? Right? We know that for such simple sentences, we can decide whether they're true or not. We know that in general, you cannot decide whether it's true. Well, somewhere in between is the boundary, right? Where is it? Where is the boundary? Might be going a little fast here, but well, if I end early, that's okay. So now the title, was about the Sigma02 degree. So we are working on this question, the question on the previous slide, for the Sigma02 degrees. So these are the E degrees of Sigma02 sets. Equivalently, these are the E degrees below the jump. Okay. Now, well, so here are some reasons why we might care about the Sigma02 degrees. These are the countable structures, by the way, right? Because there are only countably many Sigma02 sets, so there are only countably many Sigma02 degrees. Here are some reasons why we care about them. One, well, they are analogous to the CE Turing degrees. Right, so, and well, the CE Turing degrees are pretty important, so yeah. Two, in some sense, the Sigma02 degrees already reflect the global structure of the E degrees, in a sense that if you have a non-trivial automorphism of the E degrees, which we don't know, we don't know they exist, by the way. So whether such things exist is an open question, but we know that if they exist, then any such thing must also move some Sigma02 E degree. Okay, so whatever's happening sort of in the global structure, right, in some sense is reflected in this local structure here. That's a result of Slayman and Soskova. And also three, well, three is perhaps just, it's like, oh, there's something cool happening here, so we should study it, right? So there are things happening here that are somewhat unusual relative to the other degree structures that people have looked at. So I think that's a good reason to look at it, to see like, okay, well, what unusual things can happen. Okay, so now some context. So now I'm going to explain what unusual things happen in this structure. So I need to tell you about some history about results in this structure. So Cooper showed that the Sigma02 degrees are dense. Okay, so in between any two, you can find another one. And well, this is also true for the CE Turing degrees, right? In the CE Turing degrees, you have sex density, so they are dense. And so Cooper asked, well, are these two structures elementarily equivalent? Do they satisfy the same first order sentences? Right? So Cooper didn't know of any counterexample to this, and such a counterexample was provided by Ahmad. And what I'm about to show you was not Ahmad's first counterexample, but it is a counterexample. So it's the following. So Ahmad showed that in the Sigma02 degrees, you can have such a phenomenon where you have two degrees A and B incomparable, such that if you have any x that is strictly below A, then x must be below B as well. Okay, so what happens is that, well, A and B are incomparable, right? So in particular, A is not below B, okay? But once you drop below A, then you must be below B. Okay, that's the phenomenon that's happening here. Now, what does this have to do with Cooper's question? Well, it gives one answer to Cooper's question, namely, notice that in such a pair, which we call an Ahmad pair, so A and B we call an Ahmad pair, A cannot be the joint of 2 degrees below it. Why is that? Well, suppose that you have 2 degrees below A, such that they join up to A. So say X and Y. Okay, so X and Y are both strictly below A. Now, because of this property, X and Y are both below B, right? And if X and Y are both below B, well, then their joint is also below B. So their joint cannot be A, right? Because A is not below B. So that's the proof of this statement here. And that stands in contrast to what happens in the CE Turing degrees. Because in the CE Turing degrees, you have stack splitting, right? So every CE degree splits into 2 below it. In fact, it even splits as sets and so on. So this is an elementary difference between the structures of Sigma02 degrees and the structure of CE Turing degrees. Okay, so that's kind of the beginning of the story here. Now the question is, well, what else can happen, right? What other weird things can happen here? And that's our main result. So on the top, I just repeated the theorem from the previous slide. And at the bottom, this is our theorem. So we showed that for every incomparable A, B, and C now, so we have 3 degrees, either there is some X such that X is strictly below A, but not below B, or X is strictly below B, but not below C. Okay, so let me draw some pictures to try to illustrate what this is saying. So here's one possible scenario that could happen if you have incomparable A, B, and C. Okay, so the way I've drawn these is like, I've drawn this to suggest that A and B are an Ahmad pair. So maybe everything that's strictly below A is below B. Okay, that's possible, right? Ahmad pairs exist. Okay, but in that case, well, our theorem says that, well, then you must be able to find something below B that is not below C. Okay, so because the assumption that A and B is an Ahmad pair means that the first bullet point fails, which means that the second bullet point must be true. So that's the X in the picture. Right, so that's one possible scenario. Another scenario is maybe you have A, B, and C, and maybe A and B, so A and C form an Ahmad pair, and B and C also form an Ahmad pair. So that's kind of what is drawn in the picture, right? As long as you drop below A, you must be below C. As long as you drop below B, you also must be below C. Again, that is something that can happen. It's not, well, it's not explicitly shown by Ahmad, but it is something that can happen. In that case, well, our theorem says that you must be able to find something below A that's not below B. Okay? Because in this case, well, the second bullet point must fail, right? So the first bullet point must be true. So that we have some X as indicated in the picture. Okay, so here's that's the statement of the theorem. And later I'll say a bit about why we care about this, right? I mean, right now this is like, okay, this is one sentence it's one first order sentence in this structure, which is true. But why do we care? How does this fit into the bigger picture? That's what I hope to explain in the rest of the talk. So in our considerations later, there is actually a slight strengthening of this theorem that we will use. So actually this theorem was stated a bit too, it was a bit too specific, namely, we don't actually care that A, B, and C are incomparable. All we need for this theorem to be true is that A is not below B. Okay, so in particular, it doesn't matter the relationship between A and C. A and C could be comparable. In fact, they could even be the same. Okay, and the theorem would still be true. So, I mean, that's just our proof only uses this assumption here. So, I just put the incomparable here just so that the picture is nicer to draw, but it's true in general as well. Okay.
B not below C.
Well, so B could be below C. Well, wait, hold on. Let me see there. So, right, yeah. Sorry. Yeah, no, I should be adding that there as well. Okay. So, what do we do with this? Why do we care about this statement? First, I'd like to recast the statement in a equivalent form, just in a different kind of framework that makes it easier to discuss statements of this type. So coming back to Ahmad's original theorem, there are incomparable A and B such that if X is strictly below A, then X is below B. We can reformulate this as an extension of embeddings problem. So what that means is that, well, we're saying, okay, this A and B is an embedding of the anti-chain AB into the Sigma02 E degree, right? Because A and B are incomparable. So, and what Ahmad's theorem says is that not every embedding of the anti-chain AB can be extended to an embedding of the partial order ABX, where X is strictly below A and not below B. Okay, so if you shuffle the logic around, right, these two statements are equivalent. Similarly, we can also recast our theorem in this kind of form, except that it's not going in the other direction, in the sense that Ahmad's theorem says that some embedding fails to extend, whereas our theorem says that every embedding of something always extends. Okay, so this will look like this. Our theorem says that if you embed the anti-chain ABC, we can extend it to an embedding of one of the following partial orders. Either you can get an embedding of ABCX, where X is below A and not below B, or you can get an embedding of ABCX, where X is below B and not below C. Now, there's a bit of fine print here on the slide. So actually, what we really have is we have 4 partial orders, not just 2. Because in both points, I didn't fully specify what the partial order relations are. Like in point number 1, I didn't say how X and C are related. So depending on how they are related, we could get 2 different partial orders. And similarly, in point number 2, depending on how X and A are related, we get 2 partial orders. So actually that's 4 in total. But for the purposes of the slide, I just included these 2. Okay, so this is kind of the context in which these results live. Right? Ahmad's theorem says that some embedding fails to extend. Our theorem says that every embedding extends. Now notice here that a feature of our result is a disjunction. Okay, we are saying that every embedding extends to an embedding of one of these 2, but which choice, which embedding you extend to depends on the original embedding of ABC that you're given, right? For different choices of ABC, you might not succeed in, maybe you don't succeed in the first one, but you succeed in the second one. So there is some disjunction here. And I just like to say that this has a precedence in Ahmad's work as well. So actually, our result on no Ahmad triples, so the result that I just talked about, that theorem, it says that there are no Ahmad triples. It generalizes Ahmad's result that there are no symmetric Ahmad pairs. So what that means is the following. If you have A and B incomparable, then either you can find some X which is strictly below A but not below B, or you can find some X which is strictly below B but not below A. So this is a special case of our result, right? If you just take C to be equal to A. That's why I mentioned that earlier. So this disjunctive element already appears here. And just to kind of get us more familiar with this recasting, right, we can just rewrite this result as an extension of embeddings problem in the following way. We're saying that every embedding of the anti-chain AB can be extended to an embedding of ABX, where X is below A and not below B, or an embedding of ABX where X is below B and not below A. All right, so now with this change in language, now it makes it easier to talk about general considerations. What is the goal here, right? Remember, our goal was to find an algorithm. Well, so our goal was to find a boundary, right, between where the sentences that we can decide the true false and the sentences that we can't. So for now, what our goal is to find an algorithm to decide the 2 quantifier first order theory of the Sigma 2 E degrees. What that means is that you give me a Sigma02, no, you give me a 2 quantifier sentence, and in the language of partial orders, and I have to decide for you whether it's true in the Sigma 2 E degrees. So we know that 1 quantifier sentences are decidable, as I discussed earlier, and 2 is the next goal. Let me mention that in terms of quantifier alternations, 2 is the best that we can hope to achieve. So Ken showed that the 3 quantifier theory is undecidable. So maybe 2 may or may not be decidable, but 2 is the most we can decide, possibly, given our knowledge. Now, what does this have to do with extensions of embeddings? Well, if you give me any 2 quantifier sentence, I can reformulate it as an extension of embeddings problem. And I mean it in the, in a more general sense of having possibly disjunction. Okay, so like the disjunctions that appeared in our theorem. So therefore, right, equivalently, we want to find an algorithm to decide each of these extensions of embeddings problems, whether they can be achieved or not. For now, so this is the overall goal. For now, we are focused on the following special case, which I will call the one-point extensions of anti-chain problem, because there are several restrictions that we're making here. So here's the problem. You're given a finite anti-chain P, and we're given one-point extensions, finitely many, of P. So a one-point extension is one where you add a new element, right? So, and now the goal is, okay, can we decide whether every embedding of P into the sigma02 degrees extends to an embedding of one of the qi. So the previous results that I mentioned, right, Ahmad's theorem, as well as our generalization of it, so the existence of Ahmad pairs, the non-existence of Ahmad triples, all of them fall into this class of problems. And some history. So for n equals to 0, in other words, if there is only one extension of P that we care about, okay, if the question only gives you one choice, then actually this is already solved. Okay? So this was solved by Lamb, Stamen, and Sorby. Not even just for, without the restriction, right? So without the anti-chain and without the 1-point extension restriction is completely known. But n greater or equals to 1 is open. So it's the disjunctiveness, right, that is giving us, that presents difficulties here. Okay, so now I'd like to talk more about our progress towards this problem. And of course, the key ingredient is going to be the non-existence of Ahmad triple that I mentioned earlier. We are going to push the result further in hopes of narrowing down exactly what's possible and what's not possible. For now, we're also going to consider a further restriction here where in the 1-point extension, the new element is not above any of the old elements. So it could, the new element, like let's say you have an anti-chain, right, dot, 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 dot. And then you're adding a new element. It could be incomparable with the old ones. It could be less than some of the old ones, but it's never going to be above. Okay, that's the special case that we're looking at, which is already hard enough. So, yeah. Now, let's think about some basic considerations here. Like, what are some obvious ways in which we might try to extend embeddings, and how can we defeat all possible extensions of embeddings? So we're given an anti-chain, we're given some 1-point extensions of this form, this special form. How might we embed the anti-chain in a way that prevents embedding prevents it from extending? Well, one kind of embedding that's always going to be there is given by density. Right? By density, you're always going to be able to find something that's below some A0, let's say. You have some non-zero A0. There's always going to be something that's strictly below A0 and is not zero itself. So let's just talk a bit about that. So some notation here. Suppose we have for each of the qi, the 1-point extension, each of them, they're adding one new element, right? So let's call that new element xi. So q0 would be a0 dot 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 ak as well as x0, for example. Okay. And well, so let's just say that xi is below aj in the order qi. Just if it's assuming it's below something, well, let's call it something aj. Well, then we know that given any aj degree, any degree aj, by density, we can always find some non-zero xi that's strictly below it. So, well, the question now is, is this actually an embedding of qi? Right? I mean, so far it seems to check out, right? The xi is below aj in qi. And in terms of degree, well, xi is actually below aj, right? So far it seems to check out. But don't forget about the other aj primes, right? We have to make sure that those relations are also true in order for this to actually be an embedding. So the question now is, well, whether this defines an embedding of qi, well, it depends on the set of j prime for which xi is below aj prime. It has to kind of match up, right, with whatever qi says. So, but like nevertheless, so this doesn't really prove anything, but I just wanted to say that, okay, density is a thing and we have to be aware of it. Okay, now let's talk about some necessary conditions that we have. And these are obtained by considering these special one-point extensions. So these are the extensions that, they play a very important role in deciding whether we can actually extend, at least, as far as we can tell. Suppose that in Qi, we have xi below aj, and xi is not below any of the other aj prime. Okay, so it's below aj, it's not below all of the others. So such Qi, we call them singleton extensions. Okay, and they play an important role in our analysis because, well, let's see what happens here. Okay, first of all, if there are no singleton extensions, what does that mean? Well, that means that for all of the Qis, the xi must be below at least 2 aj's, right? That's what it means to not be a singleton. Well, then we can easily prevent those extensions from happening by making A0 to AK pairwise minimal pairs. So that is something that we can do in the E degrees. A minimal pair is something where you have two things which are not zero, and anything that's below both of them must be zero. So using that, we can block all of these extensions. So the case where there's no singleton extensions is easy to handle. Now, what if there are singleton extensions? Well, how do we deal with them? So if we have some anti-chain that doesn't extend to an embedding of Qi, well, then what does that say? That means that everything that is strictly below aj must be below some other aj prime, right? Because if it were not below any other aj prime, then it would be an embedding of Qi, right? And hopefully this looks familiar because this is exactly the kind of thing that's happening in Ahmad pairs. Except with the difference now is that in Ahmad pairs, there is like a single aj prime such that every x below aj is below aj prime. Whereas here, we don't actually care that there is a single aj prime. As long as there's some aj prime out there, right, such that x is below it, that's fine. And for different x, there might be different aj primes. So this is a kind of a more general notion here. If aj has such a property, then we say that it's a weak Ahmad base. So a special case comes from Ahmad pairs. So if A and B form an Ahmad pair, then A is a weak Ahmad base. It's just an example, which is just shuffling the definitions. And it's natural to wonder, well, can we have weak Ahmad bases which don't come from Ahmad pairs? And we show that indeed you can. So not all weak Ahmad bases come from Ahmad pairs. So that is I would say, the second main theorem of our paper. Okay, now, so this is the part where, this is the part where the paper ends, and now the next paper begins, right? The next paper, which has not been written, begins. So now we're going into speculative territory, going into ongoing work. Yeah. Okay, so weak Ahmad bases. Now we want to understand them more, okay? Because, well, I mean, because of this property here, right, on the slide. If you have some singleton extension and you fail to extend to that, then you have some kind of weak Ahmad base floating around. So the question now is, well, what kinds of degrees can be weak Ahmad bases? And the reason why we want to understand this is because, well, just in the previous slide, we only looked at like a single Qi. We said, okay, here's a singleton extension. If we fail to extend to that, what happens? But in general, you have many singleton extensions, and you have many extensions that are not singletons, and you want to prevent extensions to all of those, right? So that means that essentially it's like we have to combine several requirements. That's a rough intuition here. So in order to see whether this is achievable, to see when this is achievable, we have to understand which degrees can be weak Ammon bases. And here's a theorem that we are pretty sure that we have proved. So if A and B form an Ammon pair, then B cannot be a weak Ammon base. And this generalizes our result on no Ammon triple, because no Ammon triple says that if A and B form an Ammon pair, then B and C, where C is anything that's not above B, cannot form an Ammon pair. So, and remember that if B and C form an Ammon pair, then B is a weak Ammon base. So that's why this is a generalization. So this helps us understand, what kinds of degrees can be weak Ammon bases. In fact, we believe that we have proved the following stronger statement, which I will call star. And I'm not going to call it a theorem because, we don't know whether we've actually proved it. I mean, we think we have, but, it needs to be checked. Let's talk about what this is. So suppose we have A0 ... AJ, incomparable, and all of them are weak Ammon bases. Then for each I, there is some xi below ai, so that xi is not below any of the other ai prime. Okay, so this guy, well, what's the relationship between this guy and the previous in the theorem on top? Well, this implies the theorem on top, and here's how. Right, so just consider the case where J is 1. So we only have A0 and A1. If we take A0 to be A, like the A in this theorem, and A1 to be B, the B in this theorem again, then I claim that this star statement implies the theorem. Okay. Why? Well, consider this A0 and A1, in other words, A and B. Now, if A and B form an Ammon pair, then A is a weak Ammon base. If B is also a weak Ammon base, then by star, you must be able to find something that's below A, but not below B. And that contradicts the assumption that A and B was an Ammon pair, right? Ammon pairs say exactly that such things cannot happen. So that's the proof that star implies the theorem. And so we believe we have proved star, but yeah, again, needs to be checked. The question now is, okay, now star, I claim, is going to help us give some useful necessary condition for embeddings to fail to extend. And here's how. So suppose that we have some anti-chain of degrees A0 to AK, which fails to extend to any of Q0 ... Qn. Okay. Now, just for ease of notation, for Q0 ... Qn, well, some of them are singleton extensions, maybe, right? So we just put all of them at the front. So the singleton extensions come first. And also we can rearrange the anti-chain because it's an anti-chain, right? So you can push it around. So we'll just say that, and in the beginning, like from Q0 all the way to Qj, all of those Qis at the beginning, the new element xi lies below ai, and it doesn't lie below any other ai prime. So previously I was like, oh, let's say that xi is below aj, but just for ease of notation, I don't want to have too many letters floating around. So I'm just assuming that xi is below ai. And we can assume this just by rearranging the anti-chain. Well, so now, right, by the reasoning in the previous slide, because the anti-chain doesn't extend to an embedding of each of the Qis for I less than or equal to j, that tells us that A0 ... AJ, they are all weak Ammon bases. In other words, everything that's strictly below, say, A0 must be strictly below some other ai prime. Well, if we have a bunch of weak Ammon bases, then we can apply star on the previous slide to say something about it. So assuming star, then for each I less than or equal to j, we can choose some xi below AI, which is not below AI prime. Now, here is the scope of AI prime is very important. These AI primes are the ones that are less than or equal to J. Okay, so it's like you have a bunch of singleton extensions at the beginning, and for each of them, you can choose something below it that is not below any of the other like singleton extension things. Okay. However, each of these xi that we just chose, they must be below some aj prime, right? They must be below something else because they must be a weak gamma base, right? So you know we've just said that they are not below any of the beginning AI primes, so they must be below some of the later aj primes. Otherwise, we could just we could use xi to extend the embedding. Furthermore, we could consider the other QMs as well. So far, we've just been considering like each of the singleton extensions QI, but how about the non-singleton extensions? Well, now they cannot be, right? So we cannot extend to an embedding of QM by using xi. So this equivalence cannot be true. That's just a rephrasing of that statement. Okay, so all of this, I know it's like notationally very heavy, but the point here is that now we can use this to formulate some kind of combinatorial condition that only depends on the orderings QI. And the hope is that that's going to tell us exactly whether embeddings can extend or not. So here's how the condition looks like. So again, this is a lemma, assuming that star is true. If there is an embedding of the anti-chain A0 to AK, which does not extend to any of the QI, then there must be a function, nu. Okay, so what is nu? Well, so nu is going to be defined on the set of I such that QI is a singleton extension. And nu I must have the following properties. So first, nu I must be a non-empty subset of 0 to the 0 dot 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 to k minus the domain of nu. Okay, so what's the intuition here? Think of nu I as the set of j prime such that xi is below aj prime. Okay, from the previous slide. So nu I is recording that set. And so that motivates why condition 2 is a thing, right? We need to say that there is no QM such that I union nu I is exactly the set of j prime, such that xm is below aj prime. So this here, right, regardless of why this is true, you can see that this is a purely combinatorial condition that only depends on the partial order. Right? So this is the kind of thing that we are hoping to get. Well, what we're hoping is that we get some equivalence, right? So right now we only have a necessary condition on this side, but if we can get an equivalence, then then we would have an algorithm. Let's do an example just to get an idea as to what this lemma is saying. So let's consider the case where k is just 1. So we have A0 and A1, 2-element anti-chain. So here's a fact that every embedding of the anti-chain A0 and A1, it extends to an embedding of one of the following two orderings, Q0 and Q1, where Q0 is a singleton extension where the new element X0 is below A0 only. So the new element X0 is below A0 and not below A1. Q1 is not a singleton extension. So Q1 is adding a new element X1 where X1 is below both A0 and A1. Okay, so why is this true? Well, so this is like, it's easy to prove this separately, not using the lemma, but I'll just do it using the lemma just to illustrate how this goes. So in order to show that every embedding of this must extend, I need to show that there cannot be such a function nu, right? So then I can use the lemma. So why is there not such a function nu? Well, by point number one, like what are the possibilities for nu zero? Well, nu zero has to be a non-empty subset of the set 0, 1 minus the singleton 0. In other words, it's a non-empty subset of the singleton 1. So that's the only, the singleton 1 is the only choice for nu 0. But now, if we define nu 0 to be the singleton 1, then we violate condition 2 now, because, well, on the left-hand side, we're going to have 0, 1, and on the right-hand side, we're also going to have 0, 1, because in Q1, x1 is below both a0 and a1. So this is a trivial special case of the lemma. I just put it to show you how these kinds of things work. Okay, now it turns out that we know that this condition is not sufficient. Okay, so this is a necessary condition, but we know that it's not sufficient. But we can beef it up, right? So our analysis can be, pushed further to get a better necessary condition. Here's recalling the basic setup here, just the notation from 2 slides ago. We have an anti-chain, A0 to AK. It doesn't extend to Q0 Qn. And we put the singleton extensions at the front. So these are the Qi for I less than or equal to j. And by star, we have chosen for each I less than j, some xi, which is below ai and not below ai prime for any I prime below j. Now, what can we do here? Consider the joint. Okay, there's a joint, right? In this upper semi-lattice, we have a joint. So consider the joint of xi and xi prime, where I and I prime are distinct. And now the point is, well, the set of j prime such that the joint is below aj prime is exactly the intersection of the set of j prime such that xi is below aj prime and the set of j prime such that xi prime is below aj prime. Right? That's how the joint works. You take the intersection. So that forms a new constraint that this function nu must satisfy. It must also play well with the intersection. And so this intersection, right, it cannot be realized by any QM in a sense that we need to make sure that if we take this and we extend the embedding using this, then it doesn't become an embedding of any of these. Right? So, and of course, here I took the join of 2 things, right? But you can take the join of any of the singleton extensions, right? Any of those, you're going to get a similar kind of analysis. So I won't show you the actual condition here because it's not super long, but it's not so easy to understand. But basically, using that, we now have a working conjecture. So we believe that once we soup it up using this intersection reasoning on the previous slide, then we can write down some combinatorial property of nu, which characterizes exactly when anti-chains fail to extend. And so if this is true, right, if this actually is a sufficient condition, then this would give us an algorithm for deciding whether every embedding of a given anti-chain P extends to an embedding of some Qi, where the Qi's are one-point extensions, where the new element is not above any old element. So I'm just repeating the question here that we are hoping to solve. So again, details need to be checked here, and this is a working conjecture, so we're happy to revise it, if new phenomenon comes up. But yeah, that's all that I have for today. Thank you.
So any questions?
Oh, give that.
You mentioned that not every weak gamma base comes from a math pair. How do they look? How, yeah, how would other type of weak gamma base look like?
Right. Okay. So yeah, just repeating in case the online people couldn't hear. But the question was, how do these weak Ahmad bases which don't come from Ahmad pairs, how do they look like? Well, the point is that in an Ahmad pair, you have like A0, A1, where everything strictly below A0 is also below A1. Well, in a more general thing, you could have A0, A1, A2, and everything below A0 is either below A1 or below A2. But for different axes below, there might be different. Some of them are below A1 but not A2. Some of them are below A2 but not A1. Yeah, so that's how it looks like. Yeah, and yeah, like we didn't prove it explicitly, but you can do the same for finite remaining.
Other questions?
Is the I might have missed this, but the three quantifier theory is undecidable. Is that correct?
Yeah, by Kent. Yeah.
Okay, and then it does what's the complexity? Is it just sigma 1 or we know?
I don't know. Yeah, I think you're not the first person to have asked this question, and I think in general, yeah, it seems that figuring this out seems to be hard. So I don't think people have really tried.
I don't think it's a prime, Peter, because I mean, just think of the complexity of irreducibility between sigma 02, that's like sigma 4, 5, whatever, and then they add 3 more quantifiers, right? So now you get an upper bound, 0, 0, 7, or something like that. I'm not sure you can get that much better. I mean, maybe you can get it down to 0 something, but it's not going to be 0 prime. I doubt that. Because I mean, because basically what you do adding parameters, right? So deciding the zero, deciding the 3 quantifier theory is not the same thing as one jump over deciding the 2 quantifier theory.
Yeah.
Thanks, Stefan. Yeah, I'm definitely not an expert in this because I didn't read the proof that 3 quantifiers is undecidable. Yeah.
Well, I mean,
yeah,
I had to because I was advised.
Right. Yeah, so, yeah.
Anyone else? If not, let's thank Jun again.